What types of detection cues are used for sound localization? Have you ever wondered how we pinpoint where sounds come from? Sound localization is the process our auditory system uses to determine the origin of sounds in our environment. This ability is essential for navigating spaces, understanding conversations in noisy areas, and maintaining awareness of our surroundings. The brain interprets differences in sound signals arriving at each ear, and these differences are categorized into three main types of detection cues. The first type is called interaural time differences. This cue refers to the slight difference in time it takes for a sound to reach each ear. When a sound comes from one side, it arrives at the nearer ear a fraction of a second earlier than at the farther ear. The brain detects these tiny time differences, often just a few microseconds, and uses them to figure out the direction of the sound. This cue is particularly effective for low-frequency sounds, as longer wavelengths allow for more precise timing comparisons. Next, we have interaural level differences. This cue involves the difference in sound pressure level that reaches each ear. When a sound comes from one side, it will be louder in the ear that is closer to the source and softer in the ear that is farther away. This happens due to the head shadow effect, where the head blocks some of the sound energy. Interaural level differences are especially useful for localizing high-frequency sounds, as these frequencies are more easily diminished by the head. The third type of cue is known as spectral cues. These cues arise from how the outer ear, head, and torso shape the sound spectrum before it reaches the eardrum. The structures of our body cause frequency-specific filtering, which varies depending on whether a sound is coming from above, below, or from the front or back. The brain learns these spectral patterns to help determine the elevation and front-back position of sounds. When combined, these cues allow the brain to create a three-dimensional map of auditory space. The integration of interaural time differences and interaural level differences helps with horizontal localization, while spectral cues assist with vertical localization and resolving whether a sound is in front of or behind us. Understanding these cues is also important in the context of hearing loss. Damage to the auditory system can make it difficult to detect or process these differences, leading to challenges in localizing sounds. For example, unilateral hearing loss, which affects one ear, can disrupt access to these binaural cues, complicating sound localization. Hearing aids and cochlear implants aim to restore some of these cues, but replicating natural binaural processing is complex. In conclusion, the primary detection cues used for sound localization are interaural time differences, interaural level differences, and spectral cues. Together, they enable precise spatial hearing, which is vital for effective communication and safety in our daily lives.